Okay. In the previous lecture, we have completed last 18 lectures, 18 to 19 lectures. We have completed 2 units, that is unit number 1 and unit number 2. That is from section 1. Unit number 1 is Introduction to Satellite Communication, and unit number 2 is Satellite Subsystems. And today we'll start unit number 3, that is Satellite Link Design. Okay, that is section 1, and third unit is Satellite Link Design. Okay. The unit number 3 is satellite link design. This link design we have seen in mobile communication also. I think you have remembered, you have seen uplink design and the downlink design. Okay. In the uplink design, there we have seen from, that is from mobile station to base station to mobile station. But in this uplink, we have seen from earth station to the satellite, and the downlink is from satellite to earth station. How they are designing the particular uplink and particular downlink. The same process is carried out in this also, but they are using some of the formulas and the equations to calculate the particular uh, designing for a satellite. How much is the uplink for designing the satellite, and how much is the uplink downlink for designing the satellite. They are going to calculate the particular total received power, the total transmitted power, and the resistance, and how much is the distance from earth station to satellite, and they are going to calculate the wavelength. Everything they are going to calculate by using a satellite link design. Okay. The syllabus structure is like this. Content of the syllabus is, first is introduction about this satellite link design. In this introduction, in this content, they are going to mention a basic transmission theory. This basic transmission theory you have studied in mobile communication also. The basic transmission theory is nothing but you have to calculate the total received power. That is some of the equations it is coming. And system noise temperature. This system noise temperature you have studied in analog communication. System noise temperature you have studied in analog communication. In that analog communication, we have seen a signal to noise ratio. You have calculated the signal to noise ratio of a particular amplifier. That is system noise temperature. And there is a mistake, that is G by T ratio. That is actually G is the gain and T is the transmission. That is G by T ratio. And design of uplink and the design of downlink. In the design of uplink and design of downlink, what you have seen, that is of uplink is from earth station to the satellite, and the downlink is from satellite to the earth station. In this designing, we are going to see the number of losses, and we are going to see the number of gains. Number of losses present in a particular signal, number of gains present in a particular signal. That we are going to see in this uplink and downlink. You have seen number of losses, that is propagation loss, path loss, interference loss, like some of the losses. And the gain, amplifier gain, antenna gain. These are some of the gains we have seen in mobile communication. Same is repeating in this. Okay. Next, and we are going to solve some of the numericals on basic transmission theory, numericals on system noise temperature, and some of the numericals on downlink and uplink design. And you have to compare with the design of specified carrier to noise, that is C by N is nothing but carrier to noise, that is combining the carrier to interference values. Carrier to noise combined with carrier to interference values in satellite links. And combination of all these contents, finally we are going to see the system design examples. The system design examples are based on your uplink design, based on your downlink design, and your basic transmission theory, and your system noise temperature, and your G by T ratio. This is what the content of particular unit number 3, that is satellite link design. Okay. The first, we'll start with the first point, that is basic transmission theory. See here, the basic transmission theory, you already studied this derivation in mobile communication also. Okay. The basic transmission theory, design of satellite is depends on various parameters. We have seen the parameters of satellites, orbital parameters. We have seen the satellite subsystems in unit number 2. Comparison, that is combining of these two, it is going to use the basic transmission theory. The parameters required for designing of the satellite is, the first is the weight of satellite. What is the weight of satellite? It is in a tons. The particular weight of a satellite is in tons. First we have to calculate how much is the weight of the satellite. And second, the DC power generated. Whatever the batteries they are going to integrate in a particular satellite, how much power it is going to generate, they are going to see by before launching the satellite, that is DC power generation. The frequency band, third is of frequency band. The frequency band is allocated for different orbits, for low Earth orbit, medium Earth orbit, and geostationary Earth orbit. These are the three different frequency bands are going to allocate in a different orbits. One is LEO, that is low Earth orbit. Second is MEO, that is medium Earth orbit. And the last is geostationary Earth orbit, that is GEO. You have seen the frequency band. The frequency is going to allocate by one of the organization, that is International Telecommunication Union. And the most probably the frequency bands are using are C band, KU band, and KA band. What is the frequency of C band? That is of 6 by 4 gigahertz, KU band 14 by 11 gigahertz, and KA band 30 by 20 gigahertz. What is the bandwidth for C band? 36 megahertz. What is the bandwidth for KU band? 56 megahertz. What is the bandwidth for KA band? 72 megahertz. These are the frequency bands, and particularly for the bandwidth is going to allocate for a particular satellite depending on the orbit, low Earth, medium Earth, or high Earth orbit. And they are going to use multiple access techniques. This multiple access techniques is also studied in your mobile communication, that is unit number 2 in mobile communication, that is multiple access techniques. You are using, one is TDMA in mobile communication, FDMA, TDMA, SSMA, SDMA, and one more thing is the SSMA, I think. That is, in this, the multiple access techniques used are CDMA, that is code division multiple access, TDMA, time division multiple access, FDMA, frequency division multiple access. Frequency division multiple access is nothing but what? It is a continuous transmission. A particular frequency band is allocated for a single user. Okay, not considering time and the code. In time division multiple access, they are going to allocate a particular time slot to the particular user, and frequency band is fixed for all the users, that is time division multiple access. Code division multiple access, they are going to allocate a specific code to the individual user. That code will be a random code. When you are going to call for a multiple times, the code will be generated, that is a random multiple times. That is a multiple access techniques they are going to use in this satellite system, that is CDMA, TDMA and FDM. In this you are seeing the diagram, that is we are having one side is of transmitter and the one side is of receiver. Okay, transmitter is one side and receiver is other side. Both transmitter and receiver are present at the Earth station. Both transmitter and receivers are present at the Earth station. Only the satellite is present at the space. You are saying the two antennas which are going to attach to the transmitter and receiver. The transmitter is assigned by in short form, that is of TX, and receiver in short form it is received as RX. It is going to provide a transmitted power that is assigned by PT. Transmitted power is of PT and the received power is of PR. Transmitted power is of PT and received power is of PR. Whenever you are generating and producing a particular power, it is going to produce a particular gain to that particular transmitted power. So, the particular transmitted power, the gain is going to provide is of antenna gain. That is, the gain of transmitted antenna gain is of, that is GT, and the receiver antenna gain is assigned by GR. So, what are the particulars we have seen here? One is transmitter, one is receiver. These two are present at Earth station and the only satellite is present at the space. Whatever signal you are receiving from the satellite is received at the, is transmitted from our transmitter, changes frequency and received at the receiver. The particulars we are using are transmitted power PT, transmitter gain GT, received power PR and received gain GR. Okay. Next, assume that the transmitter radiates a power in watts. The power is always measured in watts. Assume that the transmitter radiates a power PT watts with an antenna having a gain. See the left side, there is a transmitter with the transmitter power is of PT and it is going to generate the transmitter antenna gain is of GT. Okay, as compared to isotropic radiation level. Okay. Next, the power flux density. The power flux density, that is PR of D. The power flux density you have to calculate. The power flux density, that is PR of D in watts per meter square due to the radiated power in the direction of antenna at the distance d meters can be expressed as. This equation is with respect to the transmitter side. This equation is with respect to the transmitter side, and from the transmitter to receiver side, how much is the distance, that is we are going to calculate. So, PR of D is equals to PT into GT divided by 4 pi D square. The total power flux density is assigned by, that is PR of D, or instead of that you are using only PR, you can use only PR. So, is equals to is the combination of transmitted power in multiplication of transmitter gain divided by 4 pi D square. D square is nothing but that is the distance between the transmitter and the receiver. The distance from transmitter to the receiver, that is distance D. Next, the product PT into GT, the product PT into GT is nothing but effective isotropic radiated power. You have seen in mobile communication same thing, that is EIRP. In short form it is called as what? EIRP, effective isotropic radiated power. How it is going to calculate effective isotropic radiated power? It is showing one diagram, that is with respect to the particular area. If they are considering one particular area, that is of A1, how much is the effective isotropic radiated power is going to generate, and that generated power is going to produce and going to produce that particular area, that is called as effective isotropic radiated power. EIRP is equals to PT into GT. Next, if the radiating aperture, that is AT, of the transmitting antenna is large compared to lambda square. Lambda is nothing but what? That is operating wavelength. Lambda is nothing but it is a operating wavelength. So GT is equals to 4 pi AR divided by lambda square. GT and GR are same, that is gain of transmitter and gain of receiver. So GR is equals to 4 pi AR divided by lambda square. What is AR? You have seen in mobile communication, that is receiving antenna of aperture. If AR is aperture of receiving antenna, then the received power at a receiver at a distance d, so received power with respect to the transmitter they are to calculate. With respect to the aperture antenna is a fixed antenna. Aperture antenna is a fixed antenna which is going to get a signal from that antenna from transmitter to the receiver. That is your aperture antenna. That is a distance d from the transmitter is the total received power, that is PR, equals to, in the previous equation you have seen, that is PR is equals to what? PT GT divided by 4 pi d square. Same equation we are using in this. So PR is equals to PT into GT divided by 4 pi d square into AR. AR is nothing but whatever the signal you are getting from the antenna, that is your aperture antenna. This aperture antenna is calculated by using the gain of particular transmitter and the gain of particular receiver. So where AR is related to receiving antenna gain, you have to calculate only a receiving antenna, not a transmitting antenna. You transmit the signal and receive the signal. Whatever the received signal is effective for your signal, that is where the aperture antenna, that is AR, is related to receiving antenna gain, that is GR. So GR is equals to 4 pi AR divided by lambda square. Write down important equations. Tomorrow I will ask you. GR is equals to 4 pi AR divided by lambda square. If it is a transmitting antenna, the equation will become what? GT equals to 4 pi AT divided by lambda square, or 4 pi AR divided by lambda square, no matter. So what you have to calculate actually? How much is the signal receiving from the aperture antenna? So you have to take outside of ER, that is aperture antenna ER. So equation will become lambda square into GR divided by 4 pi. You have to calculate the aperture antenna with respect to the receiving antenna, that is receiver gain GR. So that is your equation number 3 and equation number 4. Whatever the equation you are getting the 4 number, you have to substitute that equation in equation number 2. In equation number 2. So the Friis transmission equation, it is also called as a total received power, or it is also called as Friis FRISS. The Friis transmission equation. So PR is equals to, you have seen the PT, see the second equation, PT into GT divided by 4 pi d square. You have already calculated the equation number 4, that is AR. Substitute that equation here, that is lambda square into GR divided by 4 pi. So the final equation, what it becomes? PT into GT into GR divided by 4 pi d divided by lambda square. 4 pi, it will become what? 4 square pi square d square. 4 square pi square and d square. Instead of that, that equation is modified, that is 4 pi divided by lambda. That is above lambda is taken at below, that is to get one of the equation, that is a path loss. So the PT GT GR divided by 4 pi d divided by lambda whole square. So what is path loss equation is, where the path loss, that is LP, is the free space path loss, is equals to 4 pi divided by lambda whole square. You have to remember, take this equation. You have to be ready with the calculator tomorrow. We'll solve some of the numericals on these equations. This one is path loss, one is receiver gain. You have to calculate the aperture antenna, and you have to calculate the total received power, and based on the some of the numericals. So where the LP is the free space path loss, is equals to 4 pi d divided by lambda whole square. If you want to modify these equations, okay, in logarithmic form, in decibel value, that also you can, that is also possible. So taking log on both sides of equation number 5. Equation number 5 is what? PT GT GR divided by LP. Taking log on both sides of equation number 5. So equation number 5 is equals to PR, that is 10 log of PR equals to almost the above the top side of the equation is positive, that is bottom will become negative. 10 log of PR equals to 10 log of PT. If there is a multiplication, that becomes plus. If there is a multiplication, that becomes plus. If there is a division, that becomes minus. Remember that. If the equation is multiplication, that is becomes plus. If the equation, that equation is a division, that becomes minus. So 10 log of PR is equals to 10 log of PT plus 10 log of GT plus 10 log of GR, that is division, divided by LP is there. So that becomes minus 10 log of LP. This is, we have converted the equation number 5 in terms of logarithmic. If you want to convert that equation into decibel values or decibel equations, that is in decibel, whatever your 10 log is there, that is in decibel, that is also in decibel, that is PR in decibel watt, is equals to, what is the equation? EIRP, effective isotropic radiated power. Effective isotropic radiated power. The effective isotropic radiated power is 10 log of Pt plus 10 log of Gt. Instead of this 10 log, the normal EIRP is equals to what? Pt into Gt. The normal EIRP equation is Pt into Gt. But if you want to convert it into decibel value, that will become 10 log of Pt plus 10 log of Gt. Write down these equations. Plus Gr, 10 log of Gr is plus Gr in decibel minus Lp, minus 10 log of Lp is minus Lp in decibel. You have seen the main equation. If he may ask, you have to convert the particular equations, the final value or the final result in terms of decibels. If may ask, you have to use this formula for calculating the particular result in terms of decibels. How to calculate in terms of decibels, how to convert in terms of normal. If there is no logarithm, that is a normal result. If there is a logarithmic value, that is in decibel value. Okay. So, whatever your signal transmitting and whatever the signal you are receiving, at the transmitting side and the receiving side, there are some of the losses are going to present in a particular signal. And some of the losses we are going to mention here is PR is equals to EIRP, that is effective isotropic radiated power, already it is in decibel, plus GR, it is also in decibel. So minus, whatever the sign you are getting the minus, all this minus sign is of losses. All these minus signs are of losses. The positive sign is of gain. The positive sign is of gain and the negative sign is of losses. EIRP plus GR minus LP, the LP which loss? That is of path loss. Again we are going to add some of the losses, minus of LA. Maybe you will ask you in numerical, you will give the value of atmospheric loss value, that is LA stands for atmospheric loss. At the transmitter side, some of the losses is going to produce, that is cable loss. So that is minus of LTX, that is a transmission loss. Minus of LRX, that is of receiving loss. These are some of the gains and some of the losses present in almost all the signals. So the max we are getting 99% of signal accurate, but 0.1% of the noise should be present. 0.1% of the loss in the signal is always present. So that is we are going to use in a basic transmission theory. So this is your point number 1 in third unit, satellite link design. So write down all the equations. These equations will be useful for calculating some of the numericals. I will give you a 2 to 3 minutes to write the equations. I will dictate, you start writing the equations. The first equation is PR of D or PR is equals to PT into GT divided by 4 pi D square. Everyone has to write. Keep in mind. PR is equals to PT into GT divided by 4 pi D square. This is the total received power. And one more equation is what? EIRP, effective isotropic radiated power. Effective isotropic radiated power, EIRP, is equals to PT into GT. EIRP is equals to PT into GT. Next, the transmission gain GT, the transmission gain GT is equals to 4 pi AT divided by lambda square. GT is equals to 4 pi AT divided by lambda square. And similarly for GR, receiver gain, GR is equals to 4 pi AR divided by lambda square. GR is equals to 4 pi AR divided by lambda square. Okay. So you can calculate ER immediately for if you know this equation. So PR is equals to, one more equation, PR is equals to PT GT GR divided by LP. So the total received power PR is equals to PT GT GR divided by LP. This is one more equation. So you have to write one more equation for path loss. The path loss, that is LP is equals to 4 pi D divided by lambda whole square. 4 pi D divided by lambda whole square. That is your path loss equation. If you want, you can write remaining equation, that is to convert in decibel. Tomorrow I will give some of the formulas how to convert it into formulas into decibels. Okay. So we'll solve some of the numericals. So keep your calculator with you aside for the next lecture. Everyone has to solve the numericals. Then and then only will get understand how you understood the unit number 1 and unit number 2. Similarly, the unit number 3 is having more numericals in this. You have to calculate almost all the contents on the numericals. So you have to be with Calci with you. So everyone has to calculate, everyone has to show me the result. I will ask anyone, please ready with your answers. Please keep your Calci with you always. From next class, I will ask you the equations first. Before starting the lecture, I will ask you the equations, whatever the basic transmission equations. After that, I will tell you how to convert the particular formula into decibel value. Same process you have to follow this. After this, we'll solve 4 to 5 numericals based on this basic transmission theory. One numerical is fixed, or this derivation will come for 6 marks or for 8 marks. Derivation is fixed, or based on this derivation, one numerical will come, that is for on 4 marks or for 6 marks. So please be concentrate on this unit number 3. This is a numerical based unit. So you have to calculate, you have to concentrate on this. In the next lecture, we'll solve some of the numericals. Okay. We'll stop here. Give the attendance.